Hayat, which in Arabic means life, is the national program for organ donation and transplantation in the UAE. In 2023, more than 100 organs were donated and transplanted through the Hayat program. However, that is not enough, as more than 4,000 patients are still waiting for a precious organ to be donated. And even when an organ is transplanted successfully, it will only last between 5 to 15 years before getting rejected by the body. We can solve this by creating organs in the lab from the patient's own cells. That way, there will be no rejection, and we will have an unlimited supply of organs. However, cells when cultured outside the body are just like people after marriage. They will look and behave differently. The main reason is because we cultured them on 2D hard plastic. And because our bodies are not made up of plastic, I started culturing these cells in 3D soft gels that resemble Jell-O, the gelatin pudding. And just like my mom was mixing bananas with Jell-O, regardless of the fact that I hated that mix, I am mixing cells with these soft gels. However, cells loved it, because their shape and function were more similar to the ones found in our bodies than the ones cultured on plastics. Also, how we assemble things will affect how they will eventually work. For example, if we assemble the car by putting the wheels on the roof, it will not function properly. The same is true for our engineered organs. However, organs have a very complex architecture. And to replicate that, we use 3D printing technologies that can copy and replicate the exact structure of any image we upload, no matter its complexity. So, if you visit me in the lab, you'll find me chemically modifying these gels, mixing them with cells, and 3D bioprinting functional organs. And no, we're not there yet, but we're on our way. These 3D printed organs will not only solve the organ shortage problem in the next decade or two, but they are enabling us today to produce cheaper and safer drugs and to study complex diseases that we don't understand fully yet, like Alzheimer's disease. In Arabic, Hayat means life, and Amal means hope. And with a collaboration between scientists, engineers, clinicians, and funding agencies, we can give patients Hayat and Amal for a better future. Thank you.
Thank you, Kamil. Wow, there's been so much about health, related to health, and it just gives you so much hope for the future to see people like you doing work like this. So thank you so much. Tell us about yourself.
So I come from Lebanon, where I did my bachelor's in chemical engineering at the University of Balamand. Then I moved to the UK to do my master's, also in chemical engineering at the University of Birmingham, where I was introduced to the field of bioengineering at the same time. So I loved that field, and I decided to pursue a PhD in the field. So I moved to France, Northeast, at the University of Lorraine, where I did a PhD in bioengineering. And during my PhD, I did two research mobilities, one in Portugal and one in Harvard in the States. And then I went back to France, finished my thesis, defended everything, and then moved to the south of France, to Toulouse, to do my first postdoc in the National Research Lab. And after that, I moved here to the UAE to do a second postdoc about bioprinting. And thanks to the GPPO and the mobility grant for postdocs, I was able to go to NYU as well.
Oh, excellent.
In New York to do research this summer also.
Wonderful. It's great to know that you're able to take advantage of that program. Yeah, that's really good to hear. So it seems like one of the real innovations of what you're doing, and maybe, I don't know much about bioengineering, that's for sure, but it seems like one of the innovations, based on what you said, is this idea of moving to soft gels.
Yes.
And to sort of change that medium in which these cells grow. Was that your idea?
No, actually, that's in the whole field is using them, but I'm using a specifically modified chemically gels that we can, when we shine light, it will cross-link And actually, that gel resembles very much Jell-O because it's gelatin-based. So we do a chemical modification of that gel, and then we mix it with cells, and then we shine light so that it's stable even at high temperatures, because the gelatin will usually dissolve at high temperatures. So it will remain as a gel, and then it has a big pore size where the cells can go in and out of it, and then they will produce their own support, the cells, while this gel is degrading. So at the end, that's why there will be no rejection, because at the end, everything will be produced by the cells, by the patient's own cells. So it's 100% compatible with them.
Yeah, that's just astonishing. That sounds like such a wonderful thing. And then tell us a little bit more about the 3D printing side of it. How do you then go from these cells that are, such a good replication of the person's own DNA and cellular structures to an actual printed object?
Yeah, so
sounds like magic.
If I want to replicate the heart, for example, I cannot do it manually. Like with pipettes and trying to do all the different compartments. That's why we use like a CT scan for the patient. Then we take a scan of his heart. We just put it in the machine, transform it as a file to the machine. Then it can replicate the exact structure of what we upload there, and it will 3D print the gel with the cells mixed with it. So it will have a fully functional heart.
I see. Wonderful. Thank you very much.
Thank you. Thank you very much.